Hello and welcome. The purpose of this video is to provide you a summary of Chapter 3, Numerical Descriptive Measures. What you see in front of you is just some administrative stuff. So first of all, the quiz questions that you may or may not have after class or after watching the video will be questions from the questions in the text 10, 11, 16, 24, 25, 73, and 75. So what you'll want to do is just make sure you complete those questions and you have your notes in front of you when you answer the questions for the quiz. And the quiz will be on Blackboard broadly about those questions. And it's just really intended to be a quick check to see that you've done your homework. If you don't have the data with your textbook, the data should be on Blackboard. If you can't get the data, you need to contact me because you can't do the problems without the data. And this last bullet, please read pages 92 and 93, Writing with Statistics. I can't stress it enough, the importance of doing this. You have to read the way people write effectively about some of the stuff we're going to learn today. It is relatively simple, but applying it and breaking it down so that other people can understand it, it can be a bit of an art. Basically, we're going to talk about measures of central location, which includes percentiles and box plots. We're going to talk about measures of dispersion. We're going to talk about the Sharpe ratio and the empirical rule. We're going to talk about covariance and correlation. And we're going to have some additional practice problems that you can do if you'd like that fall at the end of the textbook. And again, that's just the quiz questions listed for you one more time. So let's talk a little bit about describing our data. So just as way of introduction, when you are writing a paper or when you are trying to get your point across with your data, you have to describe it using statistical terms. So these three measures, central locations, dispersion, and relative location, these are good keywords, key ideas that you want to keep in mind when you're trying to describe your data. You're always going to want to mention something about at least two of these, if not all three. Within measures of central location, these are the normal measures of mean, median, and mode that we all have learned about numerous times in our life. Basically, the mean is the primary measure. It's the average, if you will, of whatever your sample is. It's computed as simply adding all the numbers up and dividing by n the number of observations. So as a way of explaining how you could apply this to your own data set, I have this data set that I've worked with a lot. It's the salary for Fortune 500 executives. So I have gone ahead and computed what the mean salary is for the Fortune 500 executives. So here you can see my Excel spreadsheet, and I will have a separate video and show you how to do all the separate things I've done in this spreadsheet. But just as by way of demonstration, you'll notice here's the companies listed down the side. So it's Fortune 500. So actually, there's 409 companies here because not all of them had all the data enough to use, etc. I had to nix some. And here is the compensation by person for 2002, 3, 4, 5. It's the average compensation by person across each year, 2002 through 2011. And you can see just barely over here, let me slide it over a little further, you can see what the mean, the standard deviation, and the median are for this data set. So in here you see that I have the mean salary for an executive in the Fortune 500 is $4,901,646. Okay, so that's a useful term for us to know. Another useful term for us to know and understand is the median. The median is similar to the mean, except for it is that the number that is in the center of the data set. So for this one, I had to jockey my data around just a little bit to line it all up to demonstrate it, but I could tell Excel to just calculate the median. So what it does then is it lines all the salaries up from lowest to highest, and it picks the one in the exact center position. And in the case of these data, it's 3,373,489. Now you'll notice that these are not the same. One of the clues that we use to know if our data is quote-unquote normal is that the mean and the median ought to be equal or very close, and you'll see, you can see here that they indeed are not in this data set. Now the mode is the third way that we can look to see if our data is normal, another measure of central location. The mode is the most frequently occurring value in a data set, and my data set does not have a mode, and that's because all of the numbers are calculated, and so they're at like the 9th decimal point, so there are none that are the same. If I was to round it all up to like the tens, there would be a mode number. A mode is just simply would be in this case the salary that occurs most frequently. To review, the measures of central location are the mean, the median, and the mode. Knowing the mean and the median tells us something about our data that is important to us. It answers the test of whether or not the data is skewed, but it also enables us to know what type of statistics to use on our data. So let's go back to our executive compensation data for just a second. And I took the liberty to go ahead and create a histogram of the executive compensation data. I knew that this data would be positively skewed because the median is to the left of the mean, so I have them broadly marked here. It's not precise, but it's close. And you can see that the median is shifted and to the left of the mean, and that means that it's positively skewed, meaning it has a very long tail on one end. So that happens when you have a few very high values. So just, this is going to come up later, but I'll just tell you now, the highest salary here is someone was making $310 million a year, where the average is, $4 million. So you can see that the data is pulled way out. That's what we call a positive skew. When we have a positive skew, our mean tends to be unrealistically high. And in the case of our data, that is exactly what is the case. So those three measures are what we call, like I said, the measures of central tendency. But we can also use another method, and that is the box plot and percentiles. Percentiles and box plots are another way to interpret our data. It's a little bit more detailed way, and it enables us to get a finer grain understanding about our data. Say, for example, we wanted the 50th percentile of our data. So in the case of this problem here, just to make it easier, I decided to take a sum across all of the years in my sample and come up with a column of data. And I wanted to find out what the 50th percentile was for a sum of 10 years of data from 2002 to 2011, 9 years of data. So the way to do that is first we decide what position we want. So in this case I wanted the 50th percentile. So I take n plus 1, so I had 409 in my sample, so I add 1 to that. And then I take 50 divided by 100, and that's going to give me 205. And this 205 is important. This 205 represents the position that the 50th percentile should be in. So you have to align your data from low to high, and then you count down until you get to position 205. And that company is in the 50th percentile. And so in this case, the 200 is this KMB Corporation, Kimberly-Clark, and it's 39,922,722,000. Now remember, that's the sum over 9 years of executive compensation. Now we can apply this and find Q1, Q2, to come up with the interquartile range for a box plot. We would just be changing the P from 50 to 25 to 75, etc. So one of the applications that we use percentiles for is box plots. Excel does not make box plots, so please hear me. Do not try to make a box plot in Excel. It takes a long time, it's tedious, and it's not necessary. I repeat, it is not necessary. But it is important to understand what a box plot does, what it does for you, and you can draw them by hand. That's perfectly fine, because it is kind of an important concept, because the box plot displays the interquartile range, which is this yellow part right here. So when we do a box plot, we come up with 5 values: the minimum, the maximum, Q1, which is the first quartile, so it's the 25th percentile, the median, second quartile, 50th percentile, and Q3, the third quartile, the 75th percentile. So for my data, I did this. I have my minimum, which is 5 million, whatever, 5.8. Q1, that's the 25th percentile, 25 million. Q2, 38. Q3, 58. Max, 310. And just disregard these percentages here for a moment, because they're not really relevant right this minute. Then I created just by hand this box plot. Okay, did you hear me? I did this by hand. I just drew it on Excel. So Excel does not have an easy way to make a box plot. So if you want to spend a lot of time, you can do it, but really, it's not worth it. So here I just made a line. I put the minimum, the Q1, the Q2, the Q3, and the max. The Q2 is labeled as the median. But this tells us something interesting. First of all, this yellow part here is the interquartile range. That's important to know that that spans from Q1 to Q3, the 25th to the 75th percentile. Generally, most of the data should be concentrated in here, most of the observations. And depending on how long the whiskers are, that's why it's called a box and whisker plot, we can see where the skew is. So notice how long this one is on the right side. That's because it is very positively skewed, this data is, because we have our median is shifted to the left of the mean, and we have a lot of values out here. So what these numbers up here represent is 47% of the total. If you added up all of these salaries, you find that 47% of the total fall up here in the maximum quartile. So between 75 and 100% is 45% of the observation, or 45% of the total sum of all of the executive compensation, whereas between the minimum and Q1, only 10% lay there. And we're not talking about number of companies, we are talking about the total amount of compensation if we add it all up. So it tells us yet another thing about our data. So now we have learned a little bit about the measures of central location to include percentiles and box plots. So what I would do is stop, pause the video, and go and work on the homework problems related to percentiles and box plots. I strongly recommend that. So this is part 2 of the chapter 3 video. Now we're going to talk about measures of dispersion, range, variance, and standard deviation, and coefficient of variation. So first, let's just talk about range and variance. Most of you have probably heard of range. Range is a simple observation where you just take the high value less the low value. The range is a pretty rough evaluation of dispersion, but it is available nonetheless. The MAD is often used. That is the mean absolute difference between the mean and the observation amount. The MAD is a useful tool because it is the absolute difference as opposed to the pluses and the minuses sort of canceling themselves out. And variance. So variance is a very useful number, but it is useful not for the number it provides, but because it is necessary to have variance to calculate standard deviation. So variance is the square difference between the observation and the mean. So that way we account for the positives and the negatives because we're squaring the difference. And of course, when you square it, it becomes positive. But variance, it's important to understand, it's not really interpretable. It is a number that is not in any way related to your data set, because variance is the squared difference between the observation and the mean. But we like variance because it enables us to get to the standard deviation. So the next measure of dispersion, and the one you use most often, is the standard deviation. So standard deviation, a few things that you should know about standard deviation. First of all is it's the most used measure of dispersion. It is the square root of the variance. It is denoted like this, this sign right here. And it is, as a for the sample, we denote it just with an S. But for a population, we denote it with the sigma. Now, for this class, you generally will not have to calculate any of this by hand, but it is important to understand where it all comes from, and I'm going to show you on Excel later, but suffice to say, this is where it comes from. And the population standard deviation, we use the sigma with, and then for the sample, we just use the S. Another useful measure of dispersion is the coefficient of variation. But the coefficient of variation is only useful when you have two columns of data, or two data sets you're comparing. You would not use this if you were just trying to look at one set of data. But when you are trying to compare this data to that data, this is a very useful and often forgotten measure. So all it is the sample standard deviation divided by the sample mean. And this tells us basically how much dispersion is in our data. We have a large value, and we're talking a little bit bigger than one, not large like thousands. That means there's relatively more dispersion in sample B, say, than in sample A. That's all it tells us, is the relative dispersion between one set of data and another. So to try to illustrate this using my executive compensation data, I have created this new table. So what I did was I took the mean and standard deviation for each year of data. So in 2002, the average executive compensation was $2,721,000, and the standard deviation was 2.4 million. And you can see it sort of changes over time. It has this little dip here during the recession, and it kind of comes back up. You notice that the coefficient of variation starts at 0.91, it then goes up right through here. Notice how much it goes up, and then it drops considerably in 2007 and becomes more variable in 2008 and drops again. So if we think about what's gone on in our economy, there's a lot of things we could probably surmise about this, that everybody was doing fine, and pay kind of was less. There was less dispersion in 2002 because it was right after 9/11, but then it kind of got back normal and we got going, and right about the time that the bubble burst, as they say, and if you listen to anything on the news lately, you know exactly what I'm talking about. It dropped. Now we're talking about the relative dispersion, so some of the highs and lows probably went away, probably more just the highs. And then right about the height of our recession, if you will, it went way up, and then it dropped off and kind of come back. I can't completely explain this because it seems like this was new, this happened too early, but nonetheless, you can kind of see a trend there. So we use these numeric indicators to help us understand our data, and so you can see that this helps us understand kind of what was going on over time. And so one of the challenges in this course is using numbers like this to then describe what we're seeing. And so that's, of course, where the challenge is, and that's why I ask you to please read the Writing with Statistics, and then I do some with you as well. So that is one way, to summarize your data and with respect to dispersion, but it only works, of course, if you can compare. So we're comparing 2002 to 3 to 4, etc. Another method, the mean variance analysis and the Sharpe ratio. So I suspect you learn about this in finance, so I don't go into too much. But basically, the mean variance analysis is just a way to measure the rate of return and the risk. And then the Sharpe ratio gives us an actual method to evaluate this with one number. And with the mean variance analysis, we would need to come up with what the average rate of return is and then what the risk is. We consider both the mean and the amount of variance. But it doesn't specify a formula, and it calls the investor to sort of consider both things. And we tend to not like that. We like to have one number identifiers for things, so this is not a method that we see used a lot. The Sharpe ratio, on the other hand, is a method that gives us one number, and we can measure the extra reward per unit of risk for the investment. Now, you have to have the mean return of investment, and you have to have the mean risk, the R, and then the standard deviation of the sample. So you've got to know all of this in order to calculate these things, which you could probably R is related to the variance, etc. But nonetheless, in the homework problems related to this, they do provide these things for you, and I don't expect you to calculate the Sharpe ratio for any of your own data, just because it could be difficult to come up with the R bar, but in some places it's specified, so if you know what that is, go for it. Anyways, using the metals and the income funds, which is, the data set that they use kind of throughout this chapter, they're comparing the metals to the income, and they find that 0.56, the metals fund offers more reward per unit of risk compared to the income fund. So useful, again. Another useful method. Now we're going to turn our attention to relative location. So within relative location, we have two theorems. This first one, Chebyshev theorem, this one you won't hear me talk about too much. The second one, I have a whole nother video on the normal distribution that hopefully you've already watched. If you haven't, you need to do so. The other one is kind of the LeBron James of statistics, as I explained in, I think was chapter 1. You have to know the empirical rule, but this one here is not as often, we don't see this quite as often. But basically what this says is that 75% of the observations are within 2 standard deviations of the mean. Now, with the empirical rule, it's slightly different, and we'll get into that in a second. For any data set, 89% of all observations will fall within 3 standard deviations of the mean, and we can calculate this for any large data set. So generally, this will work even if our data is very skewed. So it can be useful. And I have here an example that you can try. You have a class of 280 students. The mean score on an exam is 74 with a standard deviation of 8. How many students score between 58 and 90? Well, K, that's the number of groups, is going to be 2. So we have 1 minus 1 over 2 squared, which is 0.75. So at least 75% of 280 students or 210 students should have scored between 58 and 90. So then we can see if our test is, kind of within boundaries. Now, let's move on here to the empirical rule. This one you see much more often. Like I said, I have the whole other video about it. Basically, you know this probably by now, the middle 1 standard deviation is 68%, the middle 2 standard deviations is about 95%, and 3 standard deviations is 99.7%. I say here about 100% because it's pretty darn close. We like all of this because this lets us know how dispersed our data is. So remember, we're talking about measures of dispersion. This is important because this helps us understand our data better. So we always want to use the empirical rule to test our data to see if our data is normal. We do this by computing z-scores. So z-scores let us know where our data fall within the normal distribution. And indeed what we want, if we go back here, is our data, we want 95% of our numbers to fall between 2 standard deviations, like, a lot. We want it to be densely populated here. If we don't have that, if it's too what we call skewed, we have to be aware of this and do different methods. So we don't need to worry about that. But you need to understand that this method is an important way to check our data to see if our data is normal. So a score of, say, a z-score of, say, 1.25 would indicate that a sample value is 1.25 standard deviations away from a mean, while a negative 2.43 would indicate that it's 2.43 standard deviations away from the mean. And again, I'd like to refer you to my normal distribution video. It gets into a lot more about this. So I wanted to apply this rule to my executive compensation data. I knew that it probably wasn't normal. So what we want to do is compute the z-value for the low value and the high value. So I am using here the sum of the 9 years of data. So I took the sum, and you remember it's the same as before. So the mean is right here, 47,439,000, etc. And then what I did was I took the low value, I subtracted the mean from it, and then I took the high value and subtracted the mean from it. And you can see my z-scores are negative 3.59, which is outside the limit, and then a positive 22.72, which is, of course, way outside. So the values are not within 3 standard deviations, so our data is not normal. The answer to the question, of course, is no, it is not normal. Here is an example that I'd like you to do, and here I'm telling you that the census data tells us that the median household for 50, this is the low, this is the high, although I don't have that written in there. I guess I can type that in for you. And then the mean is this, and the standard deviation is that. And what I want to know is this data normal. And so the next slide will have a little quiz question on that. You'll want to answer it and then move on. And so here is the answer. Indeed, it is normal because both the z-values are within 3 standard deviations. Now we're going to move on to covariance and correlation. So covariance and correlation just denotes the direction of the linear relationship between two things, and then the correlation coefficient gives us the strength of the relationship. So again, these are the formulas. We'll be doing this in Excel, so you won't have to worry about that. I'll show you how to do that. But what's important about them is what's in bold. The direction of the relationship, that's why we use covariance, and then the correlation coefficient is the strength. So these numbers can range, from whatever, any number. I mean, it could be a huge number or a hugely small number, but that gives us the direction, positive, negative, whatever. And then this correlation coefficient is going to be between -1 and 1, and it's going to tell us the strength of the relationship. So, of course, if it's very close to 1, that means it's a very strong relationship. Okay, and like I've done before, I'm going to give you an example here. Here we have the executive compensation data. So first I graphed it for you so you can kind of see over time. These are, again, the average executive compensation over time for 2000, 2, 4, 6, 8, 10, etc. And you can kind of see how it goes down and comes back up again. It's what I showed you this on a different page as well. The covariance is 1.8 million. And the correlation coefficient is 0.538. So what we know is that we have a positive relationship, and it's not that strong really, because this number is 0.53, which is really not that high. You should know that this is not that high, but you don't necessarily have to know the exact interpretation, but when it's around 50, 60, 30, 40, 50, 60%, it's generally pretty low. And we'd like to see something a little higher than that, especially if you're doing a textbook problem. It's going to be probably in the 90s. So just kind of keep that in mind. And sometimes, we talk about it. Going back to the same problem that we have been looking at as we've gone along here is this covariance or correlation between metals and the income fund. And so you can run the same test here that I ran with my executive compensation, and you find out that their covariance is 351 and their correlation is 0.86. So in this one, we would interpret this as, they're pretty highly correlated. That's a pretty high number. So we can say that one affects the other, or there is a relationship between the two numbers, covariance and correlation. Okay, and finally, I want to just review for you that you really need to do these homework problems. This is the minimum number of homework problems one should do. I would strongly suggest actually doing more homework problems than what are listed. I have gone through this information very quickly. It is very familiar to me, but you need to become very familiar with all of these terms and which ones you use and why you use this one and that one. And you need to internalize it well enough that you can write about it. So I have tried to provide sort of a narrative with the executive compensation, and I will also put another thing on Blackboard where I summarize what we've done. But you have to do this for your own data. You should by now have picked a topic, and you should have a big old huge data set that you're working with. And all of the stuff we did, you should do for your data. So probably listed on here, I have practiced this and this and this, but I probably also should say summarize your own data. That will be in a different section on Blackboard. But really, having taught this class numerous times, I know that right now is where it's key. You have to get these terms down. You have to practice it. So I don't want to sound like a broken record, but really, you got to practice it. So I hope this clarifies the chapter, and I hope you can work with your data, enjoy this a little bit. At least you've got some data that you're interested in. And of course, as always, let me know if you've got questions. And I hope you found this helpful and you are able to find the related videos on how to do the Excel pieces of this.